So in this video, I'm going to go through the derivation of the general solution for an RL circuit. Just like what we saw with the RC circuit, we also have a general equation or general solution that we can use when it comes to solving for RL circuits. And usually when we look for RL circuits, we usually look for the current, but we also know the voltage given some equations or some concepts that we learned in former chapters. So how do we go about doing this? So if we began with a simple RL circuit like you're given here, let's say we can go ahead and actually use Kirchhoff's voltage law. And by using Kirchhoff's voltage law, we can actually, we'll just go ahead and go opposite of the current like so. And you can go ahead and go the other way as well. You'll end up with, well, essentially, if you go the opposite direction, you'll end up with minus VL minus VR is equal to 0. But then you can go ahead and actually just take the negative sign over to the other side, which means you get VL plus VR is equal to 0. So I'm just going to start here. So if I go ahead and actually substitute these voltage values with some equations that we already know, VL is equal to, or your voltage across your inductor is going to be L di dt, and we did that in the previous chapter, plus Ohm's law, V equals IR, like so. So just like what we did before, we're going to go ahead and essentially just isolate the I's on one side and everything else on the other. So this you're going to get minus R over L times I, and eventually you're going to get di over I is equal to minus RL times dt. So just like before, we integrate both sides like so, and then we get natural log, whoops, not limit, natural log of I is equal to minus RL t plus your constant. Go ahead and take the exponential on both sides to get rid of the natural log. And what you're left with is I of t is equal to e to the minus t over L over R. So basically what we did was we flipped this around. That's essentially what we did. And you'll see why in a second, plus A like so. Right, so the same trick we want to use is, well, we know that E of A is, and we also know that the reason why I flipped it around is because if we want to fit it in some sort of nice equation that we've seen in the past, we can see that the time constant is actually L over R. So what we're doing here is we're essentially just forcing the tau for the time constant to be on the bottom here. So with that, if we go ahead and simplify this, I of t is equal to your constant b times e to the minus t over tau. And it's funny because this is almost exactly like the other equation that we solve for the general equation for the RC circuit, right? So let me see if I can go back to the other one. So in this case, it's v of t is equal to, right here, v of t is equal to v naught times e to the minus t over tau. But in this case, we have current is equal to b times e to the negative t over tau here. Well, to finish it off, I know the other one said voltage, but essentially when I of t equals 0, what you get is you get I naught, which is equal to b times e to the 0, which is essentially equal to b. Therefore, we can make the connection that b is equal to I naught. Therefore, I of t is equal to I naught times e to the negative t over tau. Right, so just like before, that tau, now in this case, this tau is going to be equal to L over R, as I kind of mentioned before here. So one thing to note is when it comes to general solution for these RL circuits, it's essentially the same model, but then the only difference that you have to watch out for is that your time constant tau is going to be L over R as opposed to RC here. So just make sure you watch out for that.